Welcome back to CS 4803, 7643. We are looking at optimization and computing gradients. And so one thing I wanted to mention is that the next few lectures are going to get particularly mathy, and we're going to start doing vector and matrix derivatives. And this is a point where usually people feel that they don't quite understand or just tend to get dropped off, if you will. So I would strongly suggest not putting these lectures off for later. I'll also make a post on this on Piazza. So hang in there. Consider sticking on top of the material in the next few lectures, because if you get it, some of this stuff will be quite valuable in a number of domains. If you don't, there will always be this sort of hole that you're aware that, I know this topic was covered in class, but I kind of didn't get it at the time, and I mostly don't end up needing it because PyTorch and other libraries cover this for me. I know if I want to do it, I'll have to go back and look at the video materials and the lectures from Dhruv's class again. But it'll just forever remain like a hole in your knowledge. So I would strongly encourage hanging in there and sticking to these lectures and not putting off watching these videos. Now I'll make a note of this on Piazza as well for those who haven't joined it or are planning to watch it later. Okay, quick recap from last time. We defined a loss function. We talked about a regularizer and how the intuition of a regularizer was to prevent the model from doing too well on the training data. The intuition is coming from what is Occam's razor, which is amongst competing hypotheses. We should prefer to pick the simplest because that may generalize to other things. We talked about the simplest sort of regularizers, penalizing the L2 norm of the weights or the L1 norm or a combination. We will talk about some other things like dropout and batch normalization later in this class, but you will keep meeting this idea of doing things that prevent your model from doing too well on training data repeatedly in deep learning. So far, we started with linear classifiers. We talked about problems with those linear classifiers, what sort of cases are hard. We talked about how this is why a number of practitioners, shoehorn their problem into linear classifiers by expressing domain knowledge, by computing some sort of featureization or a feature extractor, and then doing linear classification in this feature space, in this hand-defined feature space. And where we're moving towards is, not extracting any particular hand-defined features. We talked about converting linear classifiers into neural networks or multi-layer perceptrons by expressing this, by chaining this weight, this matrix multiplication as a sequence of matrix multiplications interleaved with non-linearities, so that this does not collapse into a linear or cumulative linear transformation. And this idea should be reminiscent from lecture 1. This is hierarchical compositionality. This is what is the basis for hierarchical compositionality, that we have a sequence of operations happening that are converting some high dimensional input representation into perhaps lower dimensional representations that are either extracting templates or other things from this data. And we can, of course, make this as deep as we wanted to by repeating this process. We showed you an illustration of this process by drawing these things out as graphs, and you're going to see these sorts of graphs were fairly common, where the input is written out along its dimensions. There is usually some hidden vector. We will use h, the vector h, for our hidden dimensions, and you'll often see h1 or hm sort of hidden dimensions, and y1, y2 as the output layers. And each sequence of weights in between is the weight matrix. So between xi and hj, there is a wji connection between those two. We also made a loose high-level connection to biological neurons, but we emphasized that this was a fairly high-level connection, that this was a mathematical abstraction. That's why you're going to hear the term neurons and neural networks thrown around. But at this point, you should just think of these as what we're engaged in is differentiable programming, that we are not interested in really neural networks, but programs that we can differentiate through and learn parameters of. We told you about a number of activations functions, sigmoid, tanh, relu being the most popular of them, and other variants of these family of functions. Okay, so that was a quick recap of where we were. We are going to pick up on optimization and specifically gradient-based optimization. And this and the next lecture are going to get heavy into the idea of computing gradients, which is what we're going to spend a lot of time on. All right, I will quickly take a look at questions in case people have any questions at this point, but if not, we'll get started into the material for today. I don't see anything, so I'll get started. Okay, so recall that we are here in supervised learning. We have sort of a data set that has been given to us. We have defined a model class. It could either be a linear set of functions, W transpose X, or W as a matrix times X, or we've defined MLPs, multi-layer perceptrons, neural networks, whatever. This is our model class. We have defined at this point two loss functions, the hinge loss and the softmax cross entropy loss. And now really we have to get to the actual learning, which is search in the hypothesis space. We have defined, by defining an MLP or a linear classifier, we have defined a set of parameters W. We have defined how well we want to measure W with respect to a data set D. And really now all that remains is min over W loss of W, comma D. It's defined on a data set, but we only care about minimizing this with respect to our parameters. So that's the problem that we're going to be, that we're faced with. And let's take a look at this with a demo. Let's visualize this with a demo. That'll make this easy to understand. So here is the TensorFlow playground. It's a fairly nice, intuitive website that allows you to look at neural network training or this optimization process that we talked about. Okay, lots of things on the screen. Let's make things simple. So first, let's get rid of any hidden layers. What are we looking at? What we're looking at is, here is our data set on the left. It is a simple, well, let's make it even simple. Let's make a simple data set. This is just two Gaussians. There's an orange Gaussian and a blue Gaussian, just two clumps of data points. We have a fairly simple representation input x1, x2. X1, notice, is just looking at one of the dimensions. So it's blue indicates positive values, orange indicates negative values. And so this is coordinate number 1, coordinate number 2 visualized. These lines are indicating the strengths of the weights on these. So Y is the score being predicted for the positive category, this is a classification problem, two-class classification problem. And so we're converting this into probabilities by passing this. This is a two-class softmax is the same as doing a sigmoid as the output probability for one of the classes. This is weight number 1. So what we're looking at is, score is this weight times this X plus this weight times this X. These are the weights that we're trying to find. We do not know them. Initially, they are initialized randomly. We are making some guess at it. Our test loss is, some value 1.6, training loss is 1.6 as well. This is the by 2-class softmax cross entropy loss that we've defined on this. And we are just going to start the process of optimization, which in our case is going to be gradient-based optimization. And this is a loss function where both, you can't see two curves here. There's only one curve that you're looking at because the two are nearly overlapping. But we can see that these weights are changing. They change from their initial position. They are now 0.78, 0.90. The test loss has gone down to 0. Training loss has gone down to 0. We have a nice linear classifier that we have learned. This is the decision boundary. All is happy and well in the world of machine learning. Everything is working, right? We've done this well. Let's make things a bit more complicated. Let's make this into a data distribution where the positive and the negative classes exhibit an XOR type relationship. Where in the first and the third quadrant in this two-dimensional space is the first class, and the second and the fourth quadrant is the other class. We still have a two-dimensional feature space, x1 and x2. We're still going to fit a linear classifier, w1, w2, and let's start this training as well. So we're going to run this button. We're going to start this training. And we notice that this particular classifier is not doing too well. So let's discretize. So this is the current classifier decision boundary that it's learning. It's calling this entire region class 1 and the orange region class 2. And then, it's okay, but the training loss and test loss is still pretty far away from 0. And this is where sort of neural networks would come in. We would just add a hidden layer. So now we've added H, which is a hidden layer. H is a linear combination of these two features. So this neuron, what we're looking at, this coloring right now, blue being on the bottom right and orange being on the top left, this is H being visualized as a function of X. So X1 and X2. So when you put in various coordinates x1 and x2, where is H positive versus where is H negative? This is H1, and the second is H2. And we notice that these are templates as well. What they're really learning are two-dimensional decision boundaries, and then those two are being linearly combined to give this output. We haven't started training yet, and the nonlinearity here is tan H. We can change this. Let me see. We can change this nonlinearity to other nonlinearities, but let's just run this through and let's not change too many things. Let's just see what adding a hidden layer does. So we're getting, a little bit better. Our losses, notice, were in the 0.5s. Now they're better. Our test loss, of course, is higher than training loss, but we're starting to see, let's discretize the output. We're starting to see at least a curved decision boundary. Initially, it was just a linear decision boundary. This was positive. We're still not doing too well. So right about now, you would go, all right, let's throw more neurons, more hidden neurons at this problem. So let's just add a bit more, and let's start learning again. And now we see we're doing a lot better. So we went from 2 neurons to 7 neurons, and this decision boundary is nearly perfect, right? We're getting nearly all the training data points right. The train loss is lower, the test loss is lower. All is well in the world of deep learning now, or neural networks, or machine learning, multi-layer perceptrons, right? So things are working well. Notice what we could have also done is, instead of adding neurons to this hidden layer, we could have simply added more hidden layers as well, and then played around. So this is architecture search, what we are engaged in right now. For each setting of architectures, we are defining a hypothesis class. The hypothesis class consists of these setting of weights between these different layers, and optimization is this process of starting or setting these W's between the different neurons. So the question somebody asked was, so the neurons are randomly initialized. It's actually not the neurons that are initialized, it's the weights that are initialized. So W connection between this neuron and this X and all these edges that you see, those are initialized, and then they are optimized or learned by minimizing the loss function. So this is the loss function. By minimizing the loss function, we learn the strength of these connections or these W's. And notice now that we have a deeper neural network with 3 hidden layers or 4 total layers, we see a much better decision boundary. Things seem to be working perfect. We've driven the train and the test loss to 0. Like we've done perfect prediction. So it seems like there is nothing to do here. Everything is solved, except let me introduce some noise. And by noise, I mean that as soon as I add this, now you notice that this data set, so as I play around with this noise parameter, when it was 0, it was very clear that there was a XOR quadrant structure that was followed. When I bump up the noise, it seems like we seem to have, orange labels in the first quadrant, blue points in the second quadrant, and so on. So think of this as sensory observations from a particular task. You've went out into the real world, you've collected real data. There is going to be some noise around it. The underlying function is still the same. There's an XOR function that is creating this data set, but there's some noise around it. Now let's try training our same network again. Notice that we're first notice that we're having a harder time finding that XOR decision boundary. We are converging towards it, but we're having a much harder time. The loss does not seem to be driving down to 0. In fact, in this scenario, driving the training loss down to 0 is impossible, because notice that there's an orange point sitting here next to a blue point sitting there. It would be nearly impossible, depending on the precision, of getting one of them correct and the other one getting both of these correct, because you'd have to have the decision boundary pass through there. And now we have this interesting phenomena happening again of overfitting, where the training loss is being driven low, but the test loss is high. And they seem to be tracking each other pretty closely, but they diverge after a point, because this is now the network with its high representational capacity and finite amount of data is overfitting to the noise in the data set. And notice it'll keep going. Like it's trying to get all of these little noisy points correct. And so it's trying to carve out a fairly sophisticated decision boundary. And it gets worse as there is more and more noise. So in a 50% noise case, we will notice, what you would consider weirder and weirder decision boundaries, where it's trying to get each of the individual data points right, and therefore missing the high level perspective of that there is largely an XOR sort of underlying function here. And this problem gets worse as your model capacity increases. So if you had a less capable model, so this has fewer layers, you will fit less sort of weirder decision boundaries, because simply the representational capacity of this model is less than the representational capacity of a deeper network. Okay, any questions about this before we switch to the rest of the things? So this is our task today. This process of fitting or learning these parameters W that minimize this loss function, that's what our task is today. All right, I don't see any questions. I will move on. And I encourage you to play with this demo offline. Okay, so that's where we are at. Let me put this aside. And the sort of, so recall, min of L of W over W, that's our goal. And the simplest sort of algorithm that we will develop is called gradient descent. It falls into a family of algorithms called first order methods, where the first order refers to the first order gradients. Okay, so in terms of optimization, the algorithm we will develop is called gradient descent. For people who are used to optimization, for people who have, are coming in from an IS by E background or a convex optimization background, the idea that all of deep learning tends to rely on first order methods and gradient descent tends to be weird. It Because gradient descent is such a simple algorithm that most people look at that and go, surely you've tried something more sophisticated. Like, this is something that I was taught in like an intro to optimization class. Is there nothing more sophisticated that you folks are using? And turns out the answer is no, but for a variety of fairly valid reasons. You will see that second order methods and Hessian based methods tend to be too memory intensive and too compute intensive to actually be used in practice. But let's back up. Let's look at what is this algorithm that we're building towards. The algorithm that we're building towards follow this simple intuition that we can visualize this L of W. It is a high dimensional, it is a function of lots of variables, but we can visualize it as a landscape, and any particular point that we're at is a particular W. And if we could only follow this landscape down, we could find our way to a local optimum solution. L of W typically is not going to be convex, but we can at least find locally optimal solution. So what is this notion of a slope? Now, these are all things that you should be familiar with, but just as a recap, in one dimension, the derivative of a function is defined like this. It is the limit of a particular ratio. It is defined at a particular x that you'd like to compute. The limiting change in a function as a ratio of the change. This is the definition of derivatives. We are interested in functions of lots of variables. So in D dimensions, if we have L of W, in D dimensions, the object in front of us is not going to be a scalar function. The object in front of us is going to be a function of vectors, and so the object we're going to be concerned with are partial derivatives. So if we have a function f, which is let's say the function is f of x, where x is in Rd. Therefore, the function is a mapping from Rd to R. We are going to define a partial derivative of f with respect to xi as the limit as h approaches 0 of f x1 through xi plus h xd minus f of x1 through xt divided by h. So the change happens only in the ith coordinate, and we would like to know how much that change makes a difference in the function value, and this is known as a partial derivative in contrast to a total derivative, this is called a partial derivative because it's assuming that we can independently control these different dimensions xi, and that they do not, making a change to xi does not make a change to xi plus 1 or x1 or any other x, that there's no other relationships between these variables. So that's why these are called partial derivatives. And this is the visualization of them as a slope is that in one dimensions, the derivatives are giving you the slope of a tangent line. And in two dimensions, for example, you're converting the different dimensions into tangent lines along these different coordinate systems. The object that we're going to be concerned with is the gradient. The gradient of a function f, as we wrote down, Rd to R. The gradient of f is going to be this vector of partial derivatives along each of these coordinates. One particular caveat is that we will talk about whether this is a row vector or a column vector. row or column vector convention. We will talk about this in a few slides. In one convention system, the gradient is a column vector. In another convention system, the gradient is a row vector. We will talk about those convention systems in a few slides. But for now, just think of this as a collection or a list or a vector of partial derivatives along each of the directions that you're concerned with. The notation you will see is both this nabla notation and or which is also pronounced del. So del f of x. You sometimes see me explicitly write down what variable the gradient is taken under. You will also later see me use this notation where I will say it is the gradient is expressed as the partial derivative of a scalar with respect to a vector. So now notice x is a vector here and x's are scalars here. Okay. All right, so now that we have a gradient, we should know a couple of properties of this gradient. That the direction of the steepest descent. So if f is a function, the direction of the steepest descent is the negative gradient. It's the direction of the negative gradient, and the slope in any direction is the dot product of the direction of the gradient. Let's take a look at this by visualizing this. There's a question, I've been confused by this notation before. Why is it necessary to write down what variable the gradient is taken with respect to if the point of the gradient is to take partial derivative with respect to all variables? Yeah, thank you for asking that question. So this is an important question. Why am I writing down gradient, why am I specifying that I'm taking the gradient with respect to x? Well, because later I'm going to be interested in functions or loss functions, which are functions of both my data set and my parameters, and the only gradients I'll be interested in are with respect to w. So notice w is still a vector. We are still going to enumerate all dimensions of w, but we're not going to be interested in the gradient of the loss function with respect to the data set, because the data set is typically not something I get to control or optimize. There are going to be cases, certain specific applications in which you are going to take the gradients with respect to your data set and your data points, x and y. Those are very interesting applications. For visualization purposes, sometimes you take gradients with respect to x, and sometimes you want to do, for domain adaptation purposes, changes to your x that will cause change to your output. But this is the answer to your question, that typically we're going to be interested in gradients with respect to parameters of something that is function of both parameters and data. Okay, so this is what a gradient looks like. This is a two-dimensional function, w1 and w2. Those are the two axes. What I'm plotting is L of w, which is L of w1 comma w2. Let's, for simplicity, assume it's something like a constant a times w1 square plus b times w2 square plus c times w1 w2, right? It's just some quadratic. That's what I'm plotting. The heat map here, red is strongly positive. Let's say actually let's say red is negative, so that we can use this as a minimization example. And blue is positive, red is negative. And what we're looking at is, this is my current setting of w1 comma w2. There are these things called level sets. So all possible points at which L value or the loss value is constant. So at every point along this circle that I've drawn, or this ellipse that I've drawn, the loss value is constant. You will prove in the next homework that the gradient direction is orthogonal. So this is the negative gradient direction. This would be the positive gradient direction. So if what is this arrow that I'm drawing? This is this arrow of partial of loss with respect to w1, the partial of loss with respect to w2. And notice I've written a column vector here. This is still with the caveat of whether the gradient is a row vector or a column vector, but that's this direction of the positive gradient, and this is the negative gradient, the white arrow. And you will prove in the next homework that, for example, the gradient is orthogonal to these level sets, to the tangents at the level sets. And that property has this very nice implication that the gradient points in the direction of steepest ascent, the negative gradient points in the direction of the steepest descent, and so we can take a step in that direction for reducing our function. So remember, our goal is min of L of W, and the gradient is our handle on which way direction. The negative gradient is our handle on which way L reduces, or we can lower L. Okay, and so this is the actual algorithm. It's 2 lines of code. This is not a difficult algorithm. The algorithm says you want to minimize L of W. Here's what you do. You initialize W according to some function. Initialize. You can initialize them to all zeros. You do not want to do that. I will ask you that in a question in a couple of seconds. You might want to start thinking about why initializing all weights to zeros, or actually all weights to identical values, might be a bad idea. But maybe you want to initialize them to random values that are close to zero, so small random values. You initialize them, and then you write down a for t equals 1, 2, till you are exhausted, either computationally, emotionally, physically, but at some point there is a deadline, you are done, and till that point arises, you are writing down Wt plus 1 is equal to Wt, t is starting from 1, so I should start from 0. Yeah, so Wt plus 1 is equal to Wt minus eta gradient of the loss function with respect to W. So this eta is something known as, to optimization people, this is a step size. In the machine learning literature, you will often see the term learning rate. It is a scalar, it is a constant that is multiplied, something like 0.001, that is multiplied if your loss function lives in a certain regime. If it's cross entropy, for example, then you know what sort of scale your loss functions lives in. So it's something like a small constant value that's multiplied to this vector, and this is then subtracted from W. There are more sophisticated algorithms where eta is not a constant, where you have per dimension step size, and we will talk about some of them in a different lecture. But this right here is the simplest sort of gradient descent algorithm right here. Initialize, repeat till some number of times where you take a step in the direction of the negative gradient, and that step size is a constant value. All right, so this is what this phenomena looks like. Recall this is again L of W being plotted. Notice that this time it is a much more stretchy or a non-symmetric, non-isotropic, if you will, quadratic. Here's what this looks like. We're going to look at a particular point W. This is what the trajectory of that point looks like. Here's the minimum. Following this point, we are well, clearly mine was off. Maybe this is the minimum. This algorithm is making its way towards the minimum. Here is a different visualization of this. I need my pen. Or do I? Much better. Yeah, so here is a different video, which is actually showing 3 different methods. So there is a curve in the black, there's a curve in purple, there's a curve in blue. They are following 3 different trajectories. What you should notice is that this is all a visualization. You do not have typically access to this function L. You cannot draw this. The only reason why we are seeing this picture is because this is a 2-dimensional function. And so we can plot L of W1, L of W2 as this heat map, and we can plot this trajectory. What is this trajectory? Each one of these is a particular setting of W, right? So we're just tracking this trajectory over time. Typically, this is not what we can do because we are going to be optimizing functions of lots of variables, hundreds, thousands, millions. Sometimes when you hear about GPT, for example, being a billion parameter model, that's the number of parameters that we're optimizing. So there is none of this two-dimensional visualization that we can do. All we get to see are loss values over time. We get to see as a function of time or iterations or of updates, what does our loss look like? So if I had to plot, for example, the black curve that we just saw here, this seems to look like initially it made very quick descent and then it sort of saturated out. So this is, for example, actually I will want to change this. So let me make a quick change. It looks like this sort of a function. All we get to see is this sort of function. Purple, on the other hand, let's see if I can get purple. Purple, on the other hand, this was the trajectory of the purple function, of the purple optimizer or W, right? This trajectory seemed, so notice red is in L of W, red is a direction, red is a region of low values, blue is a region of high values, green is a region of medium sort of values. So initially, this purple curve went in a direction where it did not look like it was making much progress. But after a while, if you recall this video, it caught up very quickly and overtook the black curve in reaching the minimum. And I can play the video again so you can see that overtaking part. But you actually don't see the video, right? All you notice is that initially this function was not making a lot of progress. Then it makes very quick progress and then does better than the black curve. So this phenomena right here of the purple curve making very sudden progress is typically illustrated on these loss functions by sharp drop in loss values. But you do not have this sort of a visualization to understand why that may have happened. When things are not making progress in this regime, when the purple curve in this regime is not making progress, you do not know whether it's heading into a direction from which it's going to make significant improvement later, or it's going to just be stuck in that regime. You do not have access to that. All you have access to the scalar loss values as a function of time, because that's all we can look at. So just remember that you're going to be looking at loss curves a lot. Remember that there are sophisticated underlying phenomena going on that you do not have immediate visibility into. So try to keep that in mind. Okay. Almost immediately we become aware that gradient descent has a problem. We said our loss function is average over n, sum over n divided by n of the losses that we define at each of the data points plus some regularizer, which means that as soon as you have to compute the gradient of this loss, you also have to compute it for each of these data points. Gradient of sum is the same as sum of gradients because gradients is a linear operator, so sums and gradients can be swapped in and out. This is a useful property to remember. It comes from, you can show this from linearity of expectation, you can show this from linear operators being commutative, but gradient of sum is the same as sum of gradient, which means that in order to compute these gradients with respect to each parameter, you have to write a for loop over all data points. And typically the number of data points in your data set are going to be large. In CFAR, for example, you have 50,000 training examples. So this is a for loop on 50,000 examples within a for loop of iterations, right? So full sum on when n is large is expensive. And so the solution for this is an algorithm known as stochastic gradient descent, because in practice, in deep learning, we almost never implement gradient descent. Even when people say that they're doing gradient descent, what they actually mean is stochastic gradient descent. What that means is we actually approximate the full sum. So this is a sum over n we approximate it by taking a sum or over batches B. So this is where that code comes in handy. We define a batch size. You will see values which are powers of 2, but there's actually nothing special about powers of 2. It's just a convenient choice. These things typically arise as a consequence of the amount of memory on the GPU that you're using, but they're sort of computational budgets is how you define typically these batch sizes, and all it involves is writing one extra line in the function that we wrote down. So computation of gradients, step size, and updating the gradients, and now that extra line is just sample a batch from your training data. So given a data set, just sample a batch of 256 examples and just repeat everything else on your data batch as opposed to doing everything. So compute gradients only on the data batch. And this is what you're implementing in your homework. There are actually two ways of interpreting stochastic gradient descent. The implementation doesn't change, but the interpretation changes. One way of interpreting stochastic gradient descent is that this is the objective that we actually care about. The gradient computed over the entire data set. This is what we care about. And this is clearly mean over n things of the gradient of W of the loss, right? So Li, I going from 1 through n. So mean over n of the gradient at each data point. This is that expression. And what we're going to do is we're going to approximate this by taking a mean over B things, some batch of the same quantity, right? This is one straightforward, obvious interpretation that we are approximating the gradient. There is a different interpretation of stochastic gradient descent, which is that we are not approximating the gradient over your training data set. What we are doing is we are approximating a stochastic objective. And by that, what I mean is that you could actually take a different view of interpreting the loss. And notice I've hidden the regularizer here. It's because it just shows up as constants in these expectations. It doesn't, or in these mean computations, it doesn't really matter. What I could have done is I could have said that there is no training data set. There is no gold standard training data sets. What I'm doing is that the loss value is itself an approximation of an expectation. I have a random variable x and y, which I sample from a true distribution. I do not know what that true distribution is, but I know how to sample from it. And with respect to that x and y sample, a new sample that I've derived, that I've sampled, this is what I actually care about. That when I sample a new training data point, what is the loss that I'm going to pay? And what is the expected value of that loss under the data generating distribution? And what I can say is that L is itself an approximation of that. It's a finite sample approximation of what you actually care about. And if this is what you actually care about, if this is what you actually care about, then gradient of this, so if you just take a gradient of this, so gradient of expected value is the same thing as expected value of gradient of W of the loss of W comma X comma Y, right? Because the same argument, gradient is a linear operator, linearity of expectation. So you can, linear operators are commutative, you can swap those. And so you get the expected value of this gradient. So the true objective function that you're optimizing is a stochastic objective. Therefore, its gradient is a stochastic quantity. And what you're doing is you are approximating this stochastic quantity with B samples. And this B, so you are using N samples to approximate L, and you're using B samples to approximate gradient of W. But you are not approximating this intermediate quantity on those N samples, what is the gradient. So that's just a different interpretation of stochastic gradient descent, that it is a way of optimizing a stochastic objective, and therefore you are approximating, it's a B sample estimate of the gradient, which is also a stochastic quantity. That's where we are. We've given you the two interpretations, but realize that even those are interpretations. I had hidden the regularizer. There is, of course, the regularizer, and there is a gradient of the regularizer. It plays in the analysis and in practical implementation. It doesn't really make any difference, because you just have to deal with scaling of the regularizer. Because if you're going to compute these gradients not on n things but on b things, you just also have to be aware of what that the scaling is now adding up to something with b things. In practice, what criteria determine which of the two interpretations of SGT perform better? Those are just interpretations. In practice, they have identical implementations. So this question of which one does better isn't applicable because there is only one implementation. These are just two ways of doing analysis or thinking about what you're doing. Okay. And so the next thing we're going to look at, so now that we've established that we're going to do gradient-based optimization, we want to optimize a loss function, we're going to do gradient-based optimization. Gradients are going to be the primary object of interest that we're going to be dealing with. So this is why we're going to make you compute gradients by hand, and we're going to spend a lot of time in asking the question, how does one compute gradients anyway? And so there are four basic broad categories of how gradients are computed. You are familiar with a lot of them. You are perhaps not familiar with some of them. There is, of course, the old school pen and paper. So the pen and paper method of computing gradients, which is by hand. You write down a function as an expression with some variables, and you by hand derive analytic gradients or manual differentiation. You have probably heard of backpropagation in neural networks. That is why you're here. You want to learn about it. Backpropagation is a special case of something called reverse mode automatic differentiation, which is a special case of something called automatic differentiation, which is an algorithm for computing gradients. And that's good to know. Like, backpropagation is not an optimization algorithm. Backpropagation is an algorithm for computing gradients of loss functions, with respect to parameters, but other variables as well. What we'll see are computational flow graphs corresponding to neural networks. Lots of new terms. Don't worry, I will introduce them one by one. But there are two other ways of computing gradients: symbolic differentiation and numerical differentiation. So let's start meeting them one at a time. So here is our sort of flowchart of the different methods. I will zoom into them. Don't worry, you don't have to read everything right now. Let's take a look at these functions. So let's say this is our function. L1 of x is just x. Ln plus 1, apologies, Ln plus 1 is defined as 4ln 1 minus ln. So we define f of x as some L4, so the fourth, so this is a sequence. We have a recursive definition of our sequence. So this is our function: 64x, 1 minus x, 1 minus 2x squared, 1 minus 8x plus 8x squared, the whole thing squared. This is just a polynomial function. There's nothing particularly special about it. The only thing special is that I have a recursive definition of this polynomial. So this is my input. This is f of x. I want to compute the gradients. X is scalar, and I want to compute the partial of the total derivative of f with respect to x. Right? That's what I want to do. Manual differentiation is what you are familiar with, which is you just start with this as an expression, pen and paper, derive an expression which has just every single term you can expand, and it's an expression in terms of x. Notice that in manual differentiation or analytic differentiation, the input is an expression and the output is an expression as well. The output is not a program. The output is not a number. It is an expression. You can think of it as a string where x is a variable, but that's the input and the output. The APIs are different. In what is known as symbolic differentiation, this is, for example, what Wolfram Alpha or Mathematica will do for you. The input is a function, and the output is a expression. So this is a step that we have converted from an expression to a program. So this is now a program that computes f of x, right? This is it could even be a black box program, but the black box part is optional. The important part is that this is a program. You give it a value of x and it will tell you a value of f of x. Those steps do not have to correspond to that expression, right? So this is a program. What symbolic differentiation will do is it will take that as input and it will give you a expression back in terms of x. This is a string or it's on an expression. Automatic differentiation is take the program as input and give me a program as output. Notice this is not the difference between automatic differentiation and symbolic differentiation is you are not giving me an expression. You are giving me how to compute f prime or del of f with respect to x. You are giving me a program that I can feed as input any particular value of x, and it will return to me the partial derivative or the total derivative in this case, because it's a scalar of f with respect to x. So the input is a program and the output is a program. Numerical differentiation has the same API. The input is a program and the output is also a program or a value. The only difference between these two is that automatic differentiation is exact and numerical differentiation is inexact or approximate. Everything else that we've looked at above so far is exact. They compute exact gradients. So the only approximate gradient technique is numerical differentiation. Okay, so that's the high level 10,000 feet overview of the four techniques. Manual differentiation, pen and paper, expression in, expression out. This is the same effort, input output API as manual differentiation, except it's done by computers. This is typically done by humans. This is typically done by computers. Automatic differentiation, program in, program out. And numerical differentiation, program in, either a program or a value out, and this is approximate. So that's where we're at. We have told you four different ways of doing, of computing gradients. We've just told you their names, input output APIs. We have not gotten into details. Let's get into the details of the first one, which is pretty simple, numerical differentiation. Numerical differentiation quantifies the intuition that is shown on this slide, that a point connecting two lines on a function, as those points get closer together, it approximates the tangent to that function at that point, and therefore approximating the tangent gives us the gradient, because that's what the gradient is. It is just the slope of a function at that point, right? And so this is the approximation. If we, like, instead of limit of h goes to 0, how about we just put in a small value? 0.01 is close enough to 0. That should give us the limit. That's the intuition of, oops. So this is, for example, how you'd compute it. We are at a current w. This is our parameter vector w. This is our current setting, randomly initialized or wherever we're at. This is L of w. It has a particular loss value. All that we're going to do is that we're going to add this, partial derivative. When we want to compute the partial derivative of L with respect to W1, we will just take the first dimension and we will add a small positive. This is h for us. It's close enough to 0. We will compute the loss value of x, W1 plus h, W2, blah, 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 till WD. That's going to give us a new loss value, and we're just going to say that this is L of W1 plus h to WD minus L of W1 comma WD divided by h. That's just our gradient estimate. This is 2.5 because it's 1.25322 minus this value, this loss minus this loss divided by that, and that's our approximation to this. And now I'll just repeat this for every coordinate that I want to do this in. I will just compute the L value and repeat for every coordinate, and then I'll be able to form a vector of gradients that way. It should be obvious why this is a bad idea, because if I have an L of W where W belongs to some R of, some D where D is 1 billion parameters. If that's how many parameters there are, I have to keep writing a for loop for each of these settings. I have to make a small change. I have to compute the loss value again, and then estimate this. So it's the computation of L which can get very, very slow if I have to keep doing this for every coordinate separately. Analytic gradients, numerical gradients are typically slow. They are approximate, but they are very easy to write. Think in neural networks. If you can write the forward pass of a neural network and compute the loss, then you can compute the gradient. You just run the forward pass multiple times and take the difference and subtract, and you'll be able to get the gradient. Analytic gradients, the ones that you derive by hand, for example, are typically much faster to compute because you'll get an expression that just needs to be forward propped, or that just needs to be computed once. They're going to be exact, but doing things by hand is typically going to be error prone. Some of the earlier deep learning libraries, Caffe, for example, required you that every time you defined a new layer, you had to both implement a forward prop for that layer and a backward prop for that layer. So you have to define gradients for each layer. You have to implement, so you have to first derive it by hand and then implement it in a program. Modern deep learning libraries, TensorFlow, PyTorch, do not require you to do any derivatives by hand. So at this point, if you can put together Lego blocks and compute an output, you're good. The libraries compute gradients for you automatically. For some reason, old school professors like me still make you derive gradients by hand. And you will see that both in your homework, you will see in this class, in the next lecture and so on, we'll just be doing gradients by hand. And the answer for why we make you do that, the first sort of answer is it builds intuition. When you run into problems with gradient descent type methods, when you write a new loss layer, when you write a new layer in your architecture, it will help to know if you can, sanity check it, or that have you written a well-behaved loss function or a well-behaved layer. If you can derive the gradients by hand, you'll see certain pathological behaviors in those gradients if you can derive them by hand. And the second reason is the one that I personally like. I think it builds character. Just simply deriving gradients by hand builds character. All right, so we are at time. Let us stop here. So next time, what we'll do is we'll give you some rules for easy computation of analytical gradients. I'm hearing a lot of questions on Piazza about what is a gradient and other things. We will give you notation that we will follow in this class. And it will also serve as stepping stone towards automatic differentiation. I think the lecture on automatic differentiation will probably be one of the most math heaviest lectures on this class. And the other one is on variational autoencoders, which happens at the end of the class. Please read up on these things. Come to that lecture. You will find it valuable. We will not teach you symbolic differentiation because that's essentially not used in deep learning. It's not relevant. So we'll pick up on these points next time. We are at time. People can sign off and leave. I'm happy to stick around for a few minutes and answer questions. So thank you.